So now that we have a bit of a theoretical background on how the collision mechanism works, let's take a look at how we can apply that information to practical examples. So the first thing to mention is, and we actually mentioned this a bit later on as well, but it bears repeating, when we're dealing with primitive type collisions, there's no need to have the adaptive collision option enabled. That level of sampling really isn't necessary for primitive type collisions. So you can simply play with the actual sub-step amount and save the adaptive collisions for more actual shape type collisions. Now, when preparing your scene for actual simulation, it's important to make sure there's no interpenetration between objects before you begin the simulation. So in this case, we have the grid that's actually penetrating the bottom cubes. And what happens is, as we go to the first frame of simulation, we actually log all the different objects that are interpenetrating with each other. And it actually mentions, you get this error saying this may cause unstable behavior. So it's really important to actually make sure there's enough of a space between objects before you simulate. In this case, what I'll do is just translate this down. So it's below the object, and there's a fair gap there. That's okay. And then I will set the initial state for that. And then what you can do is actually play the simulation, let things settle, and once you see that all your rigid body objects have settled, what you can do is just select them all and then set the initial state for all the objects. And now this will become the new position for the object to start simulating, and you can be assured that there's no interpenetration. Everything is kind of sitting comfortably on top of one another. Another thing to mention is the normal direction is important when doing your rigid body collision calculations. So for example, on a grid, it might react properly where the normals are facing upwards, but you might have problems on the other side. And the same stuff with the sphere that's, say, cut in half, a bowl holding marbles. You want to make sure you invert the normals on the actual sphere so the collisions work properly. And you need to keep that in mind when you're rendering, because obviously for rendering, you may want the normals facing the opposite direction. So in that case, you might need to use a proxy for rendering and another for the actual rigid body simulation. Another point to mention here is the fact that when you use a grid, obviously a grid is very thin, so it has basically no thickness. So when an object penetrates it for a collision, there's a greater risk of having unstable results because there's no actual thickness, so that collision can occur very quickly and the object can actually pass through the grid. So you often will get fine results, but it's suggested to use cubes rather than grids with a little bit of thickness, and that tends to give a little more stable results in terms of collisions. So if we return back to our scene here and adjust these substeps, we can take a look at what kind of effect that has on the actual collision detection. So let's just bring the substeps to 1. So that means 1 sample per frame. And let's play that back. So now what's happening, you can see it quickly breaks apart. Since we're only taking 1 sample a frame, it's basically taking a snapshot per frame. So possibly one of the legs can actually penetrate through the board and go on the other side and return back to its original position in that one frame if it's very fast moving. And the sample could have completely missed that collision, so you'll get a very inaccurate result. Also, what we can do is get forces that are, say, moving in one direction because they've been pushed that way. And because we only sample it once per frame, it can inherit a lot of velocity and start traveling in that way and not be very controlled. So you get this kind of exaggerated effect, cumulative effect over the frames because there's not enough samples. Forces get out of control and they kind of tend to break apart the rig, as you can see here. So as we start introducing more samples per frame, let's go to 2. What we're doing is more accurately modeling the collisions and everything. So things get a bit more stable, a little more muted. Forces don't tend to get out of hands. Collisions get caught at the right moments, so they actually work quite well. So 2 is fairly good. And as we go up, you'll see progressively the quality of the simulation gets better and better. So we can go up to something like 5. And generally what I'll do is I'll set my my substeps to about 8 or so, just for previewing and making sure everything works roughly. It's a good idea when you're finally ready to render, bring up the substeps, Some normal ranges can see, anywhere around 50 to 60. That's not really out of hand. And then what you can do is cache the simulation to the mixer once you've generated it. And then once you have that plotted result, you no longer have to resimulate, but you have a high quality simulation that's been generated. Now, one thing to keep in mind is when collisions are detected, the system exerts a sort of force to kick it out, kick the penetration out, so it actually collides rather than interpenetrates. So that collision, that kicked out force is being applied at the next time step. So what happens is we increase the sub-steps is we're basically decreasing the time periods or the time steps. So for that reason, when you might have things that kind of collide and they kind of explode, and a lot of times that's because the time steps are very small, and then the kick force that's being applied to push that object away has to be applied over that time step. So you get a large force being applied over a small time period, and that results in this kind of exploding effect. So one thing you can do is, if you're seeing that happening, is to reduce the sub-steps to a lower level, and thereby you're increasing the time period that force gets exerted over. So you might not see as much of that popping behavior where things tend to explode. So that's just a little suggestion in terms of tuning the simulation. A quick mention here about the other collision modes like actual shape. The primitive type collisions all work fairly robustly and are fairly stable, bounding box, sphere, and capsule. Actual shape is sort of an experimental implementation. Though it can give good results, it's still sort of a work in progress. So whenever possible, of course, try and use the primitive type collisions. Now, if we look at some of the collision options, we have elasticity and friction. So elasticity obviously determines the degree of bounce an object will have with another when they actually collide. And friction is the amount it sticks when they actually collide. So if you want an object to stick more aggressively when it hits an object, what you want to do is reduce the elasticity to almost 0 and the friction to 1. So that should end up giving you that effect. And converse, if you want a sort of frictionless collision and a 100% bounce, what you want to do is set the elasticity to 1 and bring the friction down to 0. So those are a few tips and tricks for optimizing your scenes for actual rigid body collisions.